Now that we know how logical connectives or, and not play out in truth tables in part 1, you're going to learn about equivalence laws that you can check with a truth table in part 2. In this context, when I say that things are equivalent, it roughly means that they have the same truth value. So basically, they have the same end result when you compare the truth tables side by side. Side note, it is very important that you rely on your textbook for formal definitions and these videos for more informal and intuitive explanations. So to start off, notice how these two statements over here, they are logically equivalent because they have the same end result of the truth tables. So the negation of P and Q is logically equivalent to not P or not Q. So this truth table shows or verifies that these statements are equivalent, but in order to sort of prove that they are equivalent, we need to make use of the following equivalence laws. So again, we're going to look at this keeping in mind that how can we show that these two statements are logically equivalent. So the first law that we're going to learn about is De Morgan's law. So this is what De Morgan's law states. How I like to think about De Morgan's law is we're sort of distributing, for lack of a better word, the negative into the parentheses. And when we do that, we're going to negate the P and the Q, and we're also going to flip the and or the or that is between them. So once that happens, this and right here is going to be changed to an or, and in the second line, this or right here, notice how that becomes an and. The next law is the commutative law. So we have P and Q is equivalent to Q and P. And this also applies to or, so P or Q is equivalent to Q or P. Pretty self-explanatory. And now for the associative laws. The essential idea is that when we have the same logical symbol, notice how this all has ands and this all has ors, we can group the P, Q, and Rs in any order that we want using any of the parentheses. It doesn't matter, they'll still be equivalent. And for the idempotent law, we have P and P is equivalent to P, and we have P or P So these might not seem as intuitive as the other ones, but you can verify them yourself by checking them with a truth table. Now we have the distributive laws. So with these, just like the name says, they are distributive. So we're basically distributing the lone sort of element that's on the outside inside. So notice how this time the logical symbols are different. So here on the outside we have an and, on the inside we have an or, and on this one we have the or's on the outside and the and's going to be on the inside. So this is a law that you might often encounter when there's sort of test questions or homework questions. So this is an important one to sort of memorize. And then we also have the absorption laws. To save time, I'm just going to not write the equivalent. So the reasoning behind these is that you have a P or a P and Q is the same thing as P, and a P and a P or Q is going to be a P. So again, this also isn't one that is usually readily apparent, but basically the idea is that if you have a P or P, so say P is true, then because this is an or, then this statement itself is always going to be true. So now say P is false. So it doesn't matter what this whole statement is because we have an and here, and anything with an and that has a false in it, it's going to be false overall. And then with your or with something that's also false, and the overall thing is going to be false. So notice how our overall statement was equivalent to just P, because in this case, P was false. So again, with the absorption law, with the and, same reasoning here. So if P is true, then this part of the problem is going to be true. And if P is true in this or in the parentheses, because we know that P is true, then this or statement overall is going to be true. So we have a true and a true, which overall is going to give us a true. So now say P is false. Well then, because it's an and, because we know that one part of it is false, the whole thing is going to be false as well. So again, our overall statement was false, and P was also false. So the statement and just P were logically equivalent. And finally, the double negation law. Pretty simple. Not P is equivalent to P. So two wrongs make a right, sort of. And notice that because these are all equivalent to each other, if you see them in a problem or something, you can alternate between the forms. So you can expand it into a more complicated form, or you can condense it into a more simplified form. So you can go forwards or backwards. The next thing that we need to know about are tautologies and contradictions. So a tautology is always true, and a contradiction is always false. So for example, if you have P or not P, it's a tautology because it's always true. And if you have a P and not P, it's a contradiction because it's always going to be false. Now we're going to look at a couple of examples here. So use truth tables to verify the second part of De Morgan's law, which I re-put down here. So we're going to show that it's equivalent just using a truth table to verify it. So I put all of our combinations in our two columns of P and Q over here, and now we're just going to fill them out. So I like to include all of our steps, and you can include as many steps as you want, or you can just like skip steps, depending on what you feel comfortable with. But I did this to be exhaustive. So we're just going to negate whatever was in P. P or Q. And then if we negate it, we have now we're going to look at not P, so not P was false, and not Q is also false. So because it's and, it's going to be false. Oops, let me correct a mistake that I've made here. So P or Q, P or Q, P or Q. There we go. Okay, so despite the mistake, you can see that our end result, that these two statements are the same, and that we have verified De Morgan's law. Okay, our last problem that we're going to show is 1.2.12 from the text. Use the equivalence laws to find simpler formulas equivalent to this. So we're going to apply the equivalence laws that we did before and just kind of go step by step. So the first thing when you're reading this, you kind of think, okay, like where should I start? So the thing that's most readily apparent to me is this negation on the outside here. I'm going to want to use De Morgan's law to distribute sort of that in. The or switches to an and the Q is negated. And we're going to keep everything else the same. Now we're going to use the double negation law to simplify the P. Now I notice that there are certain things in common here. There's a P here, and there's a P there. So that looks a lot like the distributive laws to me. So I'm going to undistribute it. And now we can simplify actually even further by going in the reverse direction with De Morgan's law. So we have a not Q or not R. So we can simplify that by taking the negative out. And that switches to an and. And we are done. Let me just write the laws really quick so that we know what we did. At each step. And there we go. I hope that you have a better understanding of truth tables and how they relate to equivalence laws and tautologies and contradictions.